Hello friends, this is Dharmin Patel. Welcome to the lecture series of Mathematics 2. Here we will start the Laplace transformation. In this lecture we will discuss the definition of Laplace transformation of some standard functions and the Laplace transformation of periodic function. Let us start with the Laplace transformation. Here the Laplace transformation of real value function ft defined for t greater than or equal to 0 is defined as Laplace of ft, that is L of ft, is equal to integration 0 to infinity e raised to minus st ft dt. After solving this improper integration e raised to minus st ft, we get the some function of s, and this function of s denoted as phi of s or f bar s, and this function is actually our Laplace transformation of given function ft. Now we will discuss about the condition for existence of Laplace transformation. Our function ft should be piecewise continuous for all t greater than or equal to 0. Also, our function ft is exponential of order alpha. That means the limit t tends to infinity e raised to minus alpha t ft should be finite number. Now we will discuss some example related to definition. Here our example is ft equal to e raised to 2t for 0 to t and 5 for t greater than t. Now we will find the Laplace of this function ft. Our definition is Laplace of ft is equal to integration 0 to infinity e raised to minus st ft dt. Now our function ft is divided into two parts, so we can write like this: integration 0 to 3 e raised to minus st. Our ft is e raised to 2t between 0 to 3, so we are writing here e raised to 2t plus integration 3 to infinity e raised to minus st. Now our function is 5 for t greater than 3, then integration 0 to 3 e raised to minus s minus 2t dt plus integration 3 to infinity 5 common outside, then finally e raised to minus st dt. Now we integrate this term, then we get integration of this part. First integration is minus s minus 2t upon minus s minus 2, because s minus 2 is a coefficient of t and we are integrating with respect to t. Our limit is 0 to 3 plus 5 integration is e raised to minus st upon minus s, and limit is 3 to infinity. So now we will put the limit in this integration, then we get e raised to minus 3 s minus 2 upon s minus 2, and lower limit will be minus e raised to 0, which is 1, upon minus s minus 2, which is our first integration limit, plus 5 times we have a e raised to minus infinity is 0, so upper limit will be 0, minus lower limit is e raised to minus 3s upon minus s. Now we finally simplify this term, then we get e raised to, we get 1 upon s minus 2 minus e raised to minus 3 into s minus 2 upon s minus 2 plus 5 times this minus will be plus, then we get e raised to minus 3s upon s. So that is our final phi of s of our given function Laplace Here it is denoted as phi of s, and this is our Laplace of ft. Now we will see some formula of Laplace transformation. Here we have a Laplace of 1 is 1 by s, and it is obtained by definition of Laplace. Similarly, if we have any constant, then Laplace of any constant k is k by s. We have a Laplace of e raised to at is 1 upon s minus a, which is also obtained by taking definition of Laplace. Now Laplace of e raised to minus at is 1 upon s plus a. Now Laplace of cos hyperbolic at is can be written as Laplace of e raised to at plus e raised to minus at by 2, because cos hyperbolic at is e raised to at plus e raised to minus at by 2. Now we put the Laplace of e raised to at and e raised to minus at in this formula. Then finally, after simplifying, we get the Laplace of cos hyperbolic at is s upon s square minus a square. Similarly, we know that sin hyperbolic at is e raised to at minus e raised to minus at divided by 2. And now we put the Laplace of e raised to at and e raised to minus at in this formula and divide by 2. Then finally we get the Laplace of sin hyperbolic at is a upon s square minus a square. Now our Laplace of cos at is s upon s square plus a square, and Laplace of sin at is a upon s square plus a square. And Laplace of t raised to n is n factorial upon s raised to n plus 1 when n is positive integer. If n is not a positive integer, that means n is fractional number, then Laplace of t raised to n is gamma of n plus 1 upon s raised to n plus 1. We also remember that Laplace of a raised to kt is equal to 1 upon s minus k log a. Let us see some formula based examples. Here these are our examples, which are our examples of continuous function, and we will apply the direct formula of Laplace in this example. Let us see first example, Laplace of cos square 2t minus 3 e raised to 5t. Here this is our first example, which Laplace of cos square 2t minus, we separate the Laplace here, then we get 3 times Laplace of e raised to minus 5t. Now we can't find the Laplace of cos square t directly, so we apply the formula of cos square t, and our trigonometric formula of cos square t is 1 min plus cos 4t, which is the double of 2t angle, upon 2. Now our second step is as it is, and e raised to minus 5t Laplace is well known. Now we take the 1 by 2 common outside, then it can be written as 1 by 2 Laplace of 1. We know the Laplace of 1. We here apply the directly formula. Now again 1 by 2 Laplace of cos 4t and minus 3 Laplace of e raised to minus 5t. Now we know the formula of Laplace of 1 is 1 by s, so our answer is 1 by 2 upon 1 by s plus 1 by 2. We know the Laplace of cos, which is s upon s square plus a square, and we have a square equal to a is 4, so our answer is s upon s square plus 16 minus 3. Laplace of e raised to minus 5t is 1 upon s plus 5, because our a is negative here. So this is our Laplace of our function, and now we simplify it, then we get 1 by 2 common from first two term, then we get 1 by s plus s upon s square plus 16 minus 3 1 by 3 by s plus 5. That is our phi of s, which is our Laplace of given function, Laplace of cos square 2t minus 3 e raised to 5t. So now we will go to the second example, Laplace of sin cube t minus cos hyperbolic 2t. Here also we apply the direct formula of Laplace transformation. Now we will start our example. This Laplace can be written as sin cube 3t t minus Laplace of cos hyperbolic 2t. We here apply the linear property of the Laplace, and now we apply the formula of sin cube t because we can't find the direct Laplace of sin cube t. So first of all we apply the formula of sin cube t, which is 1 by 4 3 sin t minus sin 3t minus, we know the directly Laplace of cos hyperbolic t, which is applicable cos hyperbolic 2t Laplace 1 by 4 common outside and 3 also outside, then we have a 3 by 4 and Laplace of sin t minus 1 by 4 Laplace of sin 3t minus Laplace of cos hyperbolic 2t. Now we apply the formula. We know the Laplace of sin t, which is a upon a square plus a square. Here our a is 1, so our Laplace formula is 1 upon a square plus 1, which is the Laplace of sin t, and minus 1 by 4. Here our a is 3, so 3 upon s square plus 9, which is the Laplace of sin 3t, minus Laplace of cos hyperbolic t is s upon s square minus 4. Now we simplify and we are taking the 3 by 4 common from first two term, then we get 3 by 4 into 1 upon s square plus 1 minus 1 upon s square plus 9 minus s upon s square minus 4, which is our Laplace of sin cube t minus cos hyperbolic 2t, which is phi of x. So here we have a answer of second question. Now we will go to the third example, Laplace of t cube minus t raised to 5 by 4 plus 1 upon root t. Let us see how to solve this example. Here we can write this function as Laplace of t raised to 3 minus t raised to 5 by 4 plus t raised to minus 1 by 2, which is our phi of s. Now we will separate the Laplace in each term, that can be written like this. Therefore we have a phi of s equal to Laplace of t cube minus Laplace of t raised to 5 by 4, which is fractional power, plus Laplace of t raised to minus 1 by 2, which is also negative fractional power. Now we will apply the formula. Here our formula is Laplace of t raised to n equal to gamma of n plus 1 upon s raised to n plus 1 when our n does not belongs to capital N, which is positive integer set, and n factorial upon s raised to n plus 1 when n belongs to capital N, that means n is a positive integer. In the second and third part, we are applying the gamma of n plus 1 upon s raised to n plus 1 formula, and in the first part we are applying the formula n factorial upon s raised to n plus 1, that is equal to, we have a n equal to 3, so it is 3 factorial upon s raised to 4 minus, here we are applying the gamma formula. In the second part we have a gamma of 5 by 4 plus 1 upon s raised to 5 by 4 plus 1 plus, now in the last term we have a gamma of minus 1 by 2 plus 1 upon s raised to n minus 1 by 2 plus 1. So finally, after simplifying, we get this term equal to 6, that is 3 factorial upon s raised to 4, and gamma is gamma of 9 by 4 upon s raised to 9 by 4 plus gamma of 1 by 2 upon s raised to 1 by 2. As we know that gamma of 1 by 2 is equal to root pi, then we get 6 upon s raised to 4 minus gamma 9 by 4 upon s raised to 9 by 4 plus root pi upon a root s. So finally we got answer of last question is 6 upon s raised to 4 plus gamma of 9 by 4 upon s raised to 9 by 4 plus root pi by s. Now we will see the next topic, Laplace of periodic function. Here Laplace of periodic function ft with period t is defined as Laplace of ft equal to 1 upon 1 minus e raised to minus ts integration 0 to t e raised to minus st ft dt. Here we just change the integration 0 to infinity by 0 to t, and our integration is multiplied with 1 upon 1 minus e raised to minus ts, where capital T is a period of function ft. Now we will see some examples related to Laplace of periodic function. Here our example is ft equal to e raised to 3t, where our function is defined for 0 to 4 and it is 4 periodic function, which is look like as f of t plus 4 equal to ft for all t belongs to domain of t. Here our function is e raised to 3t, but we can't apply the direct formula of Laplace of e raised to 3t because our function is periodic function. So we have to apply here formula of Laplace of periodic function. Let us see how to solve it. Laplace of ft for the periodic function is given by this formula. Here formula is 1 upon 1 minus e raised to minus capital Ts, where t is the period of the function, and integration 0 to capital T e raised to minus st ft dt. Here our function is 4 periodic, so capital T is 4 and ft is e raised to 3t. Now we will put this value in formula. We get 1 minus e raised to minus 4s integration 0 to 4 e raised to minus st into e raised to 3t dt. Now we will integrate this term 1 upon 1 minus e raised to minus 4s as it is, and integration can be written as 0 to 4 e raised to minus s minus 3 t dt. Now we will integrate this term and we get finally 1 upon 1 minus e raised to minus 4s, which is as it is, and integration of e raised to minus s minus 3 t upon minus s minus 3, and limit is only 0 to 4. In the Laplace transformation we have a limit 0 to infinity, but here our limit is 0 to 4 only. Now our first term is as it is, which is 1 minus e raised to minus 4s, and so our answer is Laplace of e raised to 3t is equal to 1 minus e raised to minus 4s minus 3 upon s minus 3 into 1 minus e raised to minus 4s, when f of t plus 4 equal to ft for all t belongs to domain of f. Here our function is periodic, so we can't apply the Laplace transformation formula directly, but we have to use the formula of periodic function in Laplace transformation. In the next lecture, we will continue the Laplace transformation. Thank you very much.